my dear students. Let us continue the diffraction today. In yesterday's class, or in the last class, we discussed about in diffraction that every fringe is of different width and its intensity is also different. Okay, so today we are going to talk about intensity of how to calculate the intensity of various fringes. Okay, so intensity in diffraction is given by this formula, that is I equal to I naught sine square beta by beta square. Okay, or you can say sine beta by beta whole square. Here this I naught is the intensity of central maximum. Intensity of central maximum. Okay, what is this beta over here? Beta actually is delta phi by 2. What is delta phi? Phase difference at that particular place. Okay, so delta phi, we know that we can write in terms of delta x. We can write this as 2 pi by lambda into delta x. Okay, this cancels. So beta is coming as pi by lambda. Now delta x means what? Now if I am going to take the slit, this is the opening. Okay, single slit. And if this I am taking as d. Okay, then for this d, this delta x, we know that it is d sine theta. Correct or not? It is d sine theta. So I am writing it over here, d sine theta. So pi by lambda into d sine theta. That is the value of beta. Okay, beta is pi by lambda into d sine theta. That you have to remember. Okay, and d is the opening or the width of the slit. Okay, let's use this. First of all, we will find out I will give you the derivation of this formula, and then we are going to find various intensities in which you know now what is beta value. Okay, so let us see then how to derive this formula. Now suppose that we have an opening over here, and in this opening, in this B, I consider that there are n sources. Okay, and each one of the source is vibrating with an amplitude of E naught. Okay, E naught or A also you can say. So I am taking as E naught. Everyone is vibrating with the amplitude of E naught. So suppose, because we have to suppose here or somewhere else there is a screen. Okay, and all here there are sources. There are many sources. Okay, so if we join this with this point, like this, everyone is having one or the other phase difference. Okay, so I am joining, I am just showing you that what I am going to do actually. So like this, you can join all the points with various phase difference. Okay, and total, I have to find out what is the amplitude at this point. Alright, so see how I am going to do. Now suppose that one of these source is producing the amplitude in this direction. That I am saying is E naught. Next one in this direction. That's also E naught. Third one this. That's E naught. Then this one. That's E naught. This direction E naught. Here E naught. And one more we can say like this E naught. Okay, these are what basically at this point when you are joining it, one is going in this direction, one is going like this, one is going in this way, one is going like that. So I have joined them all. Okay, you can see that, the directions. So I have taken like this. Okay. Now I am assuming that the phase difference between the first one and the last one is delta phi. This one and this one. And suppose its phase is 0. And its phase is delta phi. Okay. Phase difference between the two I am considering as delta phi. So its phase is 0. So its phase will become what? Delta phi. Then only the difference between them is delta phi. Correct or not? So between this and this, the phase difference is what? Delta phi. So take it over here like this. Extend them like this. And extend it in this way. So what is the phase difference between the two? Delta phi. Okay. So take this as delta phi here. This is delta. Now, I am considering this to be a part of the circle. If we join them that, it is very similar to the circle. It's a part of the circle. Okay. So it's a part of the circle. Join this and take the perpendicular of this, and perpendicular of this. So perpendicular will be something like this over here, and here it will be something like this. Okay. So perpendicular to the circle here, perpendicular to the tangent to the circle. So then this will become radius. And where these radiuses will join, that will be the center surely. Okay. So since between this and this, the angle is delta phi. So angle between the two perpendiculars also will become delta phi. Are you able to understand? Angle between this line and this line is delta phi. So angle between the perpendicular of those two also will be delta phi. Okay. So this is delta phi. Now this is a circle we said. So what is the length of this arc? Length of this arc, I can say here E naught. If there are n, then I can say that n E naught is actually equal to radius into angle subtended at the center. Length of arc is equal to radius into angle subtended at the center. So what is R value here? R I can say is n E naught by delta phi. Okay, this is equation number 1. Now from here I am dropping a perpendicular on this. So this becomes delta phi by 2, and this also becomes delta phi by 2. Okay, now what is this? This actually, if suppose this is E naught, like this, if I say these are vectors, so they are the directions. Okay, and if I apply the polygon law of vectors, then this will be the resultant of all. Okay, this will be the resultant of all. I can say that this is ER, resultant of all. Okay, now what is this ER? You see this from these triangles. I can say this here, from here to here, half of ER is actually R sine delta phi by 2. ER half value is R sine delta phi by 2, and this is also R sine delta phi by 2. So total is 2R sine delta phi by 2 is equal to ER. Okay, now R value I am going to take it from here and put in this one. What's coming then? 2n E naught by delta phi sine delta phi by 2. That's ER value. Further, this 2 I will be taking over here. So what's going to become? N E naught sine delta phi by 2 by delta phi by 2. That's of ER. Now ER basically is what? This E naught was what? These are amplitudes. So ER is also what? Resultant amplitude. But if I want intensity, what we have to do? Intensity is equal to amplitude square. Okay. So resultant intensity will be this amplitude square. So IR is equal to ER square. Now what is ER then? This is ER. That will become, this I would say is maximum amplitude. Okay, so square of this will become maximum intensity. So I naught. This is sine square delta phi by 2 by delta phi by 2. Now if you remember that this delta phi by 2 we said is beta. So this formula changes into I naught sine square beta by beta square. This is the resultant intensity as far as diffraction is concerned. Okay. Now once we got this formula, now we are going to use it to find out what is the intensity of first maximum and what is the intensity of second maximum. We are already considering that the central maxima's intensity is I naught. Okay, let's see that. So this formula we got, now let's use it. So check it now. Okay, so this is here central maximum. and its intensity we have already got that, it is I naught. Okay, somewhere here is first maximum, and if you remember that for first maximum, in how many zones I have to divide this opening? 3 zones. Okay, out of that we should cancel each other, and third zone's intensity or light should reach over there, and that is only the intensity we are going to get at this position. Okay, so 3 zones. So 1 source, 2 source, 3 source, and 4 source. Okay, 3 zones I have. This I am removing right now. So this is d by 3, d by 3, and dy. Okay, join this one with this one, join this one with this one. Okay, so in this case, delta x will come what? Delta x will come d by 3 sine. Right? Now, delta x value is what? Because we are saying that this is going to produce minima over here, and this too also going to produce minima. Only this light will be there which is going to produce a light. Okay. So delta x here we are going to write as lambda by 2. Lambda by 2 equal to d by 3 sine theta. So sine theta value what we are getting? 3 lambda by 2. Okay. Now we got sine theta value. Now we have to put it into the main formula. Okay. What is main formula? Main formula resultant intensity equal to I naught sine square beta by beta square. Now beta is what? As I told you, beta is delta phi by 2. Okay, so that means 1 by 2. Now delta phi is written as 2 pi by lambda into delta x. Which delta x? Not this delta x. Which delta x? D sine. Okay, total opening. Delta x for total opening. Okay, so this is getting cancelled. Now this is pi by lambda. D sine theta. So D is as it is. Sine theta value is this. What is this value? 3 lambda by 2d. So 3 lambda by 2d. Lambda gets cancelled. D gets cancelled. So what we are getting? Beta is 3 pi by 2. Now 3 pi by 2 I am going to keep in this one now. So let us see what is the value coming for the intensity. So IR value, I naught. Now sine 3 pi by 2, when going to keep here 3 pi by 2, let's write over here. Sine square 3 pi by 2 by 3 pi by 2 whole square. So sine 3 pi by 2 means 270 degrees, and sine 270 degrees is minus 1. So minus 1 square is 1 only. So numerator will be I naught. But denominator 9 pi square by 4. Pi square value roughly we can say is 10. So 9 into 10, 90. 90 by 4. That means it will be 22.5. So you see that the maximum intensity at first maxima position, what is coming? I naught by 22.5. Central maxima I naught. First maximum I naught by 22.5. Okay. Same way, if suppose that we want to find for the second maximum, let's see, that also we find. Again I am putting here beta and here also beta. Sine square beta by beta square. Okay. Again beta is what? Delta phi by 2. That means 1 by 2 into 2 pi by lambda into delta x. This gets cancelled. Mean beta is pi by lambda. Now what is delta x value? D sine theta. Remember that. Now this sine theta only we have to find and keep in this one. So when I am going to find for the second maximum, how many zones I have to divide this opening into? After first maximum, what is going to come? Second minima. For second minima, 4 zones. So for second maximum, 5 zones. So 5 zones means this separation will become d by 5. Okay. So d by 5. So path difference in this case will become d by 5 sine theta. And again you are going to produce a condition for minima. So again this is equal to lambda by 2. So what is sine theta value? Check here. 5 lambda by 2d. 5 lambda by 2d sin theta value. That sin theta we are going to keep in this one. Put it 5 lambda by 2d here. This is 5 lambda by 2d. D gets cancelled, lambda gets cancelled, is 5 pi by 2. Okay, 450 degrees or 360 plus 90. So again, sin square theta will come as 1. But this beta square will be 25 pi square by 4. So what's going to come there? Check. So IR here is I naught. The sin square beta will become 1 pi. 5 pi by 2 whole square, that is 25 pi square by 4. As I told you that 25 is pi square is 10. So 250 by 4. So 250 by 4 means I naught by 62.5. So that is the intensity of second maximum. Okay, so that's how the intensity of every maxima from central maxima it keeps on decreasing. And if suppose we are going to make the pattern in which these intensities are going to appear to us, it will be something like this. And this is the position of central maximum, looks like this. The central maximum. This is first minima. This is first minima. Then say first maximum. This is second minimum. And after that, something like this. Okay, same way here also. And then slowly it will disappear. So this is first maximum, this is first maximum. This is second maximum. And you know that its intensity I naught by 22.5. This is I naught by 62.5. And this is I naught. Okay. So this is the pattern in which we are going to see the diffraction intensities. Okay, and as far as width is concerned, that also you know, this is 2 lambda d by d, whereas this is lambda d by d. Alright, so this is diffraction pattern. Now I am going to talk about resolution. Okay, resolution power and resolution limit of various optical instruments, including I. So first of all, what is resolution power? Resolution power is defined for optical instruments. Again I am saying including I. So resolution power of an instrument is the ability or the power of an instrument to resolve two objects which are kept close to each other. Okay? Power of an instrument to distinguish two very close kept objects. Alright, that is called resolving power, resolution power. Okay, and there is another definition which is resolution limit. Resolution limit, RL, which is inversely proportional to resolution power. What is resolution limit? The minimum distance between the two objects that can be resolved by an instrument. That's not resolving limit. What is resolution power? Is the power of an instrument to resolve two closely kept objects. Okay. So what is the resolution limit of I? I have already discussed with you. It's 1 minute. Okay. If the two objects are subtending an angle of 1 minute on the eye, then I can resolve them. Okay. But here mainly we are going to see for microscope and telescope. So what is for microscope, that we will see. And what is the criteria of resolution, that also we have to discuss. Okay, so first I will discuss the criteria, then I will come on the microscope. Criteria is Rayleigh's criteria. What Rayleigh says? Okay, Rayleigh's criteria. Now, if suppose that there is an instrument, let's say this an instrument, a lens I am going to keep. Okay, and two objects I am keeping, one here and one here. Okay, so from here let's say the light goes, okay, from here the light goes in this way, and from here the light goes in this way. We'll take it over here only. Okay, so the object here, suppose its image is like this, and this one's image is like this. Okay, image of this A and B. A is here, A dash, and B is here, B dash. So these images are overlapping each other. So is this length going to give us the presence of two objects or one object over there? Because whatever we are going to find or imagine, it is because of the images, not because of this. What is the image made by? Suppose this is I. This is I length. Okay, so what image is going to go to our brain or mind? This image. Now this image is for two objects or one object. What it is going to gain? It is going to gain it as one object. Okay, that means we are not able to distinguish these two objects as two separate objects. They are gained as, or they are received as one object. Okay, when they are going to be resolved, when we call them that we are going to receive them as two. Exactly similar thing. Again, two objects over here. Take this as. Okay. Now, like this. Suppose it's here. This one is here. Make it slightly close. Here. Okay, and another one is. Okay. Now our brain is going to take them as two objects. Okay. This will give you that two objects only. Just able to. It will be just be able to see them. They are two objects. And if suppose that we want to give perfectly two objects, that means what we have to do? These two images need to be far from each other. Something like this. A, this is B. This is one, and this is other one. This is perfectly resolved, and this is just resolved, not resolved. Okay, this is not resolved. So what is Rayleigh's criteria? Basically, Rayleigh says that whenever the light is passing through any optical instrument, a diffraction pattern is framed. Okay, a diffraction pattern is formed. So that means bending is happening. And when it is passing through the optical instrument on the other side, now if suppose this is eye, that means this place is retina. And retina we can call as field. So what Rayleigh says is, if the light from any object is passing through the optical instrument, in optical instrument there is a diffraction happening, bending is happening. Because of that bending, diffraction pattern is going to form. Okay, and in diffraction pattern obviously there is central maxima, there is first maxima, there is second maxima, all this is happening. So if suppose there are two objects, okay, because of the two objects, two diffraction patterns are forming on the screen. If the maxima, central maxima of one diffraction pattern is forming at first minima of the second diffraction pattern, then the objects are just resolved. If they are more closer, then they are not resolved. And if they are away from each other, they are resolved. I am making it right now. In that one, I will show you that what is the meaning of not resolved and just resolved. Okay. So see here, I am making two diffraction patterns. Suppose one is this. This is central maxima, this is first maxima, and this is and here also first maxima and second maxima. Another one I have made. Central maxima, first maxima. Okay, first maxima. Now you see this. This is central maxima of this one, and this is central maxima of other one. Is this central maxima forming at first minimum? No. Is this central maxima forming at first minima? No. They are very close. So they are not resolved. This you cannot see. This you will be finding as 1 only. They cannot resolve it. Okay. Now if we want to find out how will be the diffraction pattern of just resolve. Now in that one what we have to check. Again I am making 2 patterns. 1. Okay, another one. Okay, now this is central maxima and this is also central maxima. Now you see that this central maxima is forming at the minima of this one and this central maxima is forming at the minima of this one. Okay, so this is Rayleigh's criteria. This is perfect. So you say that in this condition the 2 objects are just resolved. But if suppose that they are further away, that means they are absolutely resolved. So always we are talking about this definition. Resolution limit and resolution power we are going to define for this one. Okay, you understand that? Now let us discuss about the resolution power of and resolution limit of microscope and telescope. So I am going to give you the formula. There is no derivation I am going to give for that. Okay, so resolution limit of microscope. Talking about microscope first. Okay, resolution limit. So it is 2 mu sin theta by 1.22 lambda. Okay, this mu sin theta sometimes is written as numerical aperture also. Numerical aperture. Okay, lambda there is no problem, we know that it's a wavelength. This is numerical aperture. Now what this is? This is for microscope, okay? So if this is the lens, objective, and here is the object. This is the object. Okay, and this is the lens. Now this object and this lens, in between there is a medium kept. Normally we will be keeping oil over here so that resolution limit can be increased. Okay, so mu will be kept. This is mu. Okay, and this is theta. Alright, so 2 mu sin theta by 1.22 lambda. This is the resolution limit of the microscope. Okay, same way if we are going to talk about telescope, then for telescope the same formula, resolution limit formula is 1.22 lambda by d. I think I have changed this formula. This formula is of resolution power. Okay, and resolution limit is inverse of resolution power. So this is resolution power. Okay, resolution limit will be 1.22 lambda by 2 mu sin. Okay, so here for telescope, what is the formula? 1.22 lambda by d. Okay, now in this one again, this is lambda is wavelength, you know, this is d. D is the diameter of the objective lens. We say that this is objective lens, and we know that when you talk about telescope, the rays are coming from infinity. So this theta is to be very small. Okay, and this is d. There is the diameter of the lens. So 1.22 lambda by d is the resolution limit of the telescope, whereas this is for resolution power of the microscope. Now lambda is one of the factor in both the cases. So according to the color, resolution limit or power can be changed. Now suppose that we are talking about microscope, then resolution power of which color will be more? Whose lambda is less, that means violet color. Okay, resolution power of the instrument will be more for violet color or blue color as compared to red color. Same thing is over here, resolution limit will be more for red color. Okay, because both are inversely proportional to each other. So that's all. This is for the diffraction. Okay, in the next class we'll try and solve some problems